Notice that this is a really bad title. It's catchy, but it's bad and inadequate to what I want to say. Actually, the presentation is going to be about adaptive AI. So how many AI programmers on this, in this hall right now? Howdy. Why so sad? Good, good, that's better, that's better. Okay, so I'm Piotr Trochim, and I'm not an AI programmer, which might catch you as a little bit of a surprise. I'm an animation and physics programmer, but you know, underneath all the titles, we're all mathematicians, and this is actually what I do. I'm a mathematician. And for the past year or so, I've been studying this brand new, rapidly developing field called machine learning. And I'm here to share a little bit about that here with you and sort of extrapolate onto our field that we're most familiar with. So, but onto the unfortunate title. Really, I shipped the presentation with the title and then I said, oh my God, what have I done? So what is real AI? Well, most of you, when you hear AI, you immediately jump to NPCs, and this is also what I do. But when I started prepping for this presentation, I realized that there's a lot more things we put AI into, like AI programmers even work on those things. So there's player controllers, there's multiplayer matchmaking. Our tools are getting smarter and smarter, and all of that is to aid us to help us ship better, more adaptive titles. And then that's when it hit me. It's the real AI, this thing that we're striving to accomplish, the thing that's going to be able to immerse us completely into the game worlds is not something of fiction, it's something that simply adapts. So it's the struggle to create something that adapts to our needs completely. And now, most of you are going to be thinking, okay, yeah, this is everything that we already have covered at one point or another. There is no such thing. This is a holy grail. And I'm here to argue that it's already been implemented, and the struggle here now is to push it to the games as quickly as possible so that our wonderful players can experience that. So adaptability, how do we accomplish full and total adaptability? Let's take an example, for instance. This is going to be very low level, very abstract. And if you're not an AI programmer such as myself, just try to make a mental bridge to your own field of reference. So maybe at some point somebody tried implementing a combat behavior for let's say a roguelike game or something. So you have this little situation. The green guy, that's us, the player, is facing off 3 other guys. Now, the problem that stands in front of an AI programmer is which guy do we attack first? And of course, there's plenty of ways to go about that. Myself, not being an AI programmer, would go about a distance-based method because it's simple, I understand it. So the first guy that stands in front of me, I jump at him. Oh, and of course, a disclaimer, I can only deal damage with my sword. No ranged combat. But what if those guys have different characteristics? So the guy in the back is a pretty strong mage that can instantly kill us, but he's very weak physically. We can slay him with one sword slash. And the guys standing in front of him are tanks. Our priorities would change in that case. And now this is the abstraction that I want you to start thinking about. So you've been given an innocuous, simple problem, and you've jumped to the very first, let's say, solution that came to your mind, but then requirements changed. And the requirements became a little bit obfuscated. Maybe it's not clear. So, this is something that happens to all of us, regardless of the field that we're working in. So how would you go about that? I know how I went about that, so I'm going to just, humble myself here, and people will laugh in a moment. So let's say that we have those 2 parameters. We have a distance to the guy, and we have a damage that the guy deals to us. Now our search-based method, because it's still a searching problem, which guy do we prioritize over which one? So we sort of need to come up with something, And this magnificent word that describes this coming up with is heuristics. So we do heuristics for our AI, and we try mending the data in some way, like add them with some blend weights or something like that. Anything to satisfy the purpose what the algorithm expects from us. Most algorithms, we do work with integers or floating numbers, but something, some sort of an abstraction. They're not good at working with multitude of data. But, then we implement that and everything is fine, and then requirements change again, and now faction comes into play. So we might be standing off in front of a couple of other guys, but they might be our guys. We don't want to attack them. And of course, the problem still changes. And yes, we have developed over the years a couple of technologies to counter the complexity, the ever-growing complexity of those situations, such as behavior trees, such as Monte Carlo search trees and other things like that. But at the very heart of all those things, there's still an AI programmer which needs to sift through the data that comes along and meticulously decide which is more important and how do we combine data that sort of doesn't fit into the bigger picture. So one thing to notice about this situation is that data is context sensitive. If this scene, as I pictured it before, contained the sword, then of course, a distance-based method and, looking at the stats seems fine. But again, requirements might change. We might, grab a wand and become a mage or something, and all of a sudden our behavior tree, animation programmer here, goes down the drain. We have to develop a brand new one that's gonna entail a brand new type of the behavior. What am I getting at here? I'm getting at something that constrains us from creating a truly adaptable system. We're constrained by the data that we put in the system. So we are actually, as AI programmers, doing two things. The first one, well, you guys, I'm not an AI programmer. So first of all, we're defining the data that makes the system run. The data is sort of not, intuitive to us, because it usually comes in a form of a request of our game design department. We need to have the damage and whatnot. And then we try figuring out the dependencies between that data. And that's a little bit too much. And anyone who's done, I did the sort of shippable AI once. It took me a very long time to get it right. And there were always some last-minute errors when the game finally went gold and we had to, deliver a patch. So is there another way to go about this? And of course, as you might have probably concluded from my introduction, such a way of working with data is called machine learning. And not to worry, I'm not going to go into details of all the algorithms, because machine learning is just a fancy name for algorithms, a brand new field of algorithms that came to be, well, actually have been developed for the past 15 or 20 years, but have very recently surfaced and became a mainstream. But actually, a subset of those algorithms is perfect for this situation and tackles it really nicely and does one thing that we weren't able to do before. We can stop thinking about figuring out what the data means. Instead, we can start throwing data at our system, forget about its meaning. So in this particular example that I've just shown you, what we would do is just, put all those little bits and pieces, arrange them into something we're very familiar with, a world state vector, and put it into our machine. So we'd grab all those subsequent frames, subsequent steps in the world. We would start maybe playing the game multiple times, grabbing more and more data, and just, making snapshots, how the world looked like at this point, how the world looked like at the other point. Then trying to figure out what action did the player make. This is the testing phase, and the training phase. So we're, creating a large data sets of situation that can help us understand how the situation develops. And based on that, we can say that this was a good behavior, this led to our demise, and the last one was still okay because we managed to kill the mage or whatever. and feed that through a deep neural network that will figure out the dependencies for you and then help run the AI by itself, figuring the data, figuring those little neat intricacies in the world itself. So where's the catch with this approach? Because, you know, when behavior trees were first introduced, everybody was like, well, we have finite state machines and trees are bad and whatnot. And now this new technology comes around and people are skeptical. They're still not fully confident that this might be the good thing. Apart from the obvious, which is what people usually put up against any new technology, which is stability, and you know, we want to get this thing to work like that in this particular moment, meaning predictability, which we will address later on. There's a couple of others that I wanted to address first. And this sort of brings us back around to the other part of my title, which is the timeline for when we can see this really, truly adaptable AI in our games. So the first caveat is data mining. So the main problem is how do we come up with data and what data do we come up with? So which features? Features are the fancy word for describing different parts, different components of your world state vector. So which features matter? Let's bring up the example again. So in a combat situation, what matters is how big your sword is, how much damage can it, you know, deal, how strong are you, what's your type of armor. But what's pretty unimportant is how much cash you have in your bank account, wouldn't you say? The next thing is how much data is needed. So would just, let's say, one game playthrough would be enough, or do you have to, because, you know, if you've been following up on mainstream press, you probably hear that, you know, data sets for machine learning contain of like 50 gigabytes of samples and other things like that. So how much data is sufficient? The third problem is how to collect it. So think about your game engines, like Unreal and Unity. How do you stream the data out of your engine? How do you make it accessible? And more important than that, the first boundary that I addressed, how do you forget about, you know, the limits of data? So you want to put as much data as needed, maybe even have your algorithm come up with the missing parts. Reasoning about data by an algorithm is also a top thing on the research market right now. And how do you stream it out? Where do you keep it? How do you not prevent it from impacting your FPS? Last but not least, and this one ties to practically all the others, is what kind of an algorithm, the machine learning algorithm, an actual, I don't know, deep neural network configuration or another form of reasoning bit do you employ? How do you connect them? And how does it go? How does it impact the other things? Well, as for the impact part, everything impacts everything. Your choice in the model impacts the features you're gonna be looking at and how much of that data will actually be needed. That will in turn impact how you're gonna be collecting that and what's gonna, you know, what is it going to entail. The good news is that we have skills among our teams to actually do some of those things. So data collection is what engine programmers do. Data preparation, so basically coming up with the test sets, it's what your testers can do. Or you can go procedural about it. You can create your, an example flawed AI that will do one thing, then do another thing, build a couple of test sets around that, then throw it at your neural network and have it figure out which approaches are the best, which approaches work for you. The other two, unfortunately, require a skill set from the outside world. The models is the domain of the development and research of models is in the domain of academia, mostly. It requires very deep and intimate understanding of mathematics, like something way above my pay grade level, something I'm very not good at. And feature engineering is done by people called data scientists, which in turn feel the data, let's put it this way. So they are good at telling you that the state of your bank account's not going to matter when you go into a hand-in-hand combat. Second caveat is the hardware. So the first thing, so the way we work is we work with our PCs on our desks, and this is what we're very used to. Some teams outsource, well, not outsource, use cloud computing for builds, but that's about it. With machine learning, especially with model training, you're going to have to get used to working in the cloud, especially if you're working on something a little bit more complex than the most basic of models. In more bad news, this is a snapshot taken from Nvidia page. If anybody from Nvidia is around here, I'm sorry, I'm not plagiarizing. I'm just wanting to show the recommended configuration for the training cluster, for instance. And now I would like you to take a look at this particular thing right here. It's a GPU recommended GPU accelerator called Tesla K40, which costs about $2,500 a piece. Now you can do your math and determine that this is a pretty expensive equipment. So it's sort of not something most indie game developers, for instance, would like to purchase or pursue. The very good news is that, sorry, I'm lost, that it's not actually something that you need to start working with on adaptive AI. I'm going to refer to a model, one of the training models. Actually, I've trained sets, sorry. This is the Cypher 10 set, which is used to learn, used to teach classifiers how to classify objects seen in the pictures. So it's a pretty large data set. I can't remember exactly how many data lines are in there, but here's a comparison of how fast it runs on your available set of GPUs. And the last one there is GeForce GTX 1070, practically something that everybody, each one of us has. Some people have even better graphics card at their home. And the training time drops down to 1 minute in that case. What does this mean? How do we, because for those of you less familiar with machine learning, the training of, let's say, classifier networks, and mostly working with machine learning always splits into two parts. So first, three parts. So first you develop your model or research it or whatnot, then you train it with some data set, and then you test it. Training can be conceptualized as a build. So you can think about it as just running a build, stepping out for a coffee, coming back, and the build is done, and you can start testing your neat stuff. So with GTX 1070, even a very comprehensive model can build as little as quickly as 1 minute. And even if you find yourself needing more computational power, you can always go online and outsource your code, outsource your computations to one of those are the three most popular cloud services, at least most popular to me. But there's plenty of others to go around. So hardware-wise, it gets different, but it's not impossible. Now, technology or software stack-wise, machine learning came to be in the academic environment. And academics favor, for some reason, well, the reason is pretty obvious, Python. Python for its, first of all, it's pretty lax syntax. It's a great application to rapid prototyping, and also an immense amount of libraries, mathematical libraries, that can help you build really complex models, do derivatives, do integrals in really with just a few lines of code that's really human readable. And for some reason also, I don't know why, it came to be in the Linux environment. So now most of the the most sophisticated and fancy research frameworks run in Linux and Python environment. That's a bit of a gap that to us game developers is sort of hard to jump. But most of those are already getting ported to Windows. Both TensorFlow and Theano already work on Windows with some problems on the GPU side, but those are being addressed. And then on top of that, because they can get a little bit tricky to work with when you first see them and try understanding what they do, you have simplification frameworks such as Keras, which can build very sophisticated machine learning, the most standard machine learning models for you. But this is, the good news is that this is about research. So this is in the phase where you actually are trying to, you threw data at your system and you want to have your system figure out the dependencies in the data. And this is complex, this is done offline, therefore it can be done on a different platform. What about runtime? At the end of the day, once you cooked your deep neural network, this deep neural network really looks like it's just a matrix. And it really boils down to a couple of dot products. So this is all it is there is to it complexity-wise. Dot producting a bunch of numbers, that's it. Well, there's of course the decoding and encoding phase, but let's push it out of the picture. So once you trained your network, you can pretty much recode it in any framework in any language that you are most familiar with, C++. And it runs on anything that's good with dot products, so basically that has a GPU in it, and it doesn't even have to be a very strong or beefy GPU. Just take a look at all those sample applications that can do image recognition on your phone or something like that. And of course, they don't ship to compute overseas. Okay, so that brings me to back again to the title of the presentation and the everlasting question, when? The answer is right now. It's happening right now. There are already bots that adapt to the style of play of players, to adapt to the map themselves, that exhibit real learning qualities that can generalize about really complex behaviors. I want to show you 3 examples of those, provided that there's going to be enough bandwidth. But first, to summarize, is there anything standing in the way? So first of all, the science. Science is really speeding up on the subject. The largest players, Nvidia included, Google included, Microsoft, are already on board and doing heavy, massive development in the area. So practically the Reddit for machine learning is constantly buzzing with brand new papers submitted every day or every week. So science is there. Hardware, it's there. You have access to a lot of software, all of it free. And people are already on the market. Most of those people, well, some of them, the 1/3, are already on your teams. So there's actually nothing that stops us from pursuing true adaptive AI. And the examples, I prepped for this one. The first one is the DeepMind Lab. For those of you who are not familiar, DeepMind is a company that recently made it to the media by showing off their Go playing bot that beat the Go world champion. And an example of it, of how it works in a real game environment. Okay, let's see if it's gonna play or not. Maybe not. Maybe we're not gonna be so lucky. Let's try again. Is it gonna budge now? Nope, sorry. Okay, I'm not gonna show you how it works. There are some problems with the network. The second one's pretty similar, less complex though, although it still does pretty amazing things. There's a bunch of examples online. You're gonna be able to look them up. Is OpenAI. That's a company. I think it's one of the. It's owned by that guy from SpaceX. Don't lynch me. I don't remember the name. I'm too stressed out to remember names right now. And in this particular example that I chose for sentimental reasons, it's trying to control, the AI is trying to control a moon lander and basically adapt to the ever-changing terrain and whatnot. And I also brought up a live example to show you how it looks like if you were ever trying to go about it yourself. The example shows, because there's, like I mentioned before, it's a whole range of algorithms, and some are good at one thing and the other one good at the other thing. But at the end of the day, it's about learning and how we can teach an algorithm do something that we actually like and have predictable results. So for that purpose, and for the purpose that we're going to be doing it really quickly, I chose something called a Q-learning. It's a branch of, it's an implementation of a reinforcement learning algorithm, which can be done in steps, which can incrementally show how something actually learns what we are telling it to learn, and how we can improve its understanding of the world that surrounds it. Just a sec. Yeah, that's Visual Studio for you. But the good news is that for those of you who are using 2017, they've just added support for Python back again. So, okay. To reduce noise. Okay, there are two. So this is a mouse. Yes, she's walking all over the place, and she's trying to reach cheese. It's a lesson in directions. The mouse right now is a tabula rasa. It doesn't know anything. It has no notion of the world surrounding it. This is what she sees and how she perceives the world. So this is her sight and her smell. So she basically can tell where the cheese is, the direction to it, and its closest vicinity. So what we're going to do is train her for a little while in finding cheese. Now, as it goes about it, pay attention to the chart over here. What it shows is how many steps did the mouse take to reach the cheese. As the line decreases, we can pretty much tell it converges to something common for her. So she gains understanding of this particular situation. The red line is how many steps it has taken, shows how many steps it has taken for each epoch, for each instance. The green line is just the median, just to show the general trend. So we see that she's sort of converged to a solution. We can now stop testing. Testing in Q-learning is based on having her exercise what she already knows, and then on some occasions doing a random thing, stochastical thing. And this sort of, if you recall what I said at the beginning, that the main problem that we have with those kinds of approaches is that it's not predictable. Reinforcement learning is based in stochastics, so it's not predictable. The results are not predictable. It's not very suitable for something that we want to exhibit the same behavior every time. But it's in this particular scenario, I chose it because it shows it can be shown in increments. So in this particular situation, the mouse already can find its way to the cheese. Now let's mix things up a bit. Now the cheese is on the other side, and we see that she struggles with finding her way. She sort of advances, but it's not as fast as in the other side. Now, again, the other side, it's pretty quick. She almost immediately goes there. So let's train her a little bit more. Reinforcement learning allows us to do that. This is the reason why I chose it. And let's give it a little bit of time. And there she is. Okay, it's fine. That's enough for you. So she seeks the cheese. She understands the other direction well now. Now let's see if she forgot or she retained the memory of the first one. And yep, there she is. Okay, what about other directions? Was it enough to generalize? And as it turns out, it is. Oh, by the way, she teleports back to the original starting position as she reached the cheese. Sorry for not making that clear from the start. What about going up? Again, she generalizes. What about something more sophisticated, like going in a diagonal? Well, she doesn't know the diagonal. The only actions that she can perform is going about, up, down, left, and right. Another direction. She generalizes well. All it took were 2 samples. So in this particular scenario, it's of course a very simple environment. And a very simple task to learn, but she managed to learn how to generalize directions based on just 2 samples. Now you might be thinking, of course, he's cheating, he wrote and prepped the program and whatnot. You can, the slide contains code that for the, so all of the code is on my public GitHub. So you can, you're encouraged to just go online and download it, and you can see that there's no like decision making there and whatnot. And quite frankly, there's one more awesome thing about it. I didn't need to define the actions, the directions she goes to in any particular order. I could go in, recompile, mix and match the vectors, and she would still gain intuition. So for her, I always have a problem of naming my left hand, right hand. Like this is right hand, I know, but I usually make a mistake and call it left hand. She doesn't need to know. For her, it can be left hand or it can be color red or whatever she calls it. She's still going to gain intuition based on the positive feedback that we're going to give her. And that's it. Thank you very much, and I'm looking forward to your questions.
Any questions?
Any questions at all?
Hello, thank you for the talk. So in machine learning, you're looking for a locally best answer.
Yes.
And isn't it a danger that we will create a too good AI? It would be unbeatable for player.
It's what you're referring to actually has a name in machine learning. It's called not overgeneralization. It's called extensive learning or something like that. I actually forgot the title. So what we are striving for is generalization. If you train your model on, this sort of entails to how many data samples, how many features you select, what kind of model you have selected. So basically for every kind of algorithm, it goes about in a different way. So let's take reinforcement learning, for example. There's a chance that you will have the mouse follow stuff from memory, because she's gonna create, if you throw too many like samples at her, she's just gonna repeat the same sentences. It's not gonna be able to generalize. If you take, for instance, supervised learning, like an example of a classifier, let's call it an email classifier. If you go too high on your feature vector, you're going to overtrain it. The network is going to do too good on the testing, on the training phase. It's going to get really high results. Whereas if you start putting new examples, throwing new examples at her, it's just going to go really bad. This is an example of the network going too bad. So it's and there's a whole bunch of practices that are being developed right now, along with every new data model, let's put it this way, the new network model, that teach people how to prevent those types of situations, how to go about prepping your data, how to go about teaching your network and those types of things.
Yeah, I think I have a very similar question, because I think what you actually wanted to ask about, what I understood from your question, is how do you scale the behavior of how you control, for instance, let's say that finally this machine learning is applied to actually controlling characters for behavior and so on, and many games have difficulty settings.
Yeah.
And then, I just wonder if that means that you have to make a separate training set for the different difficulty levels, or how do you scale this behavior to have different different strength of the enemy.
How smart the AI gets.
Exactly, and like so that you can control and scale the performance of the AI.
Yes, you train different models. So imagine the mental jump that one needs to make when starting to work with neural networks is pretty similar to the one physicists made when they discovered quantum physics. So instead of thinking about algorithms as controllable pieces, you don't control them anymore, and they become like black boxes for you. So yes, you throw data that you want to throw at them. For instance, the combat scenario. If I wanted my AI to be really stupid and just go at the first guy in front of me, I'd prep a test set that would exude this behavior, exhibit this particular behavior. Going about it, of course, in a noisy way, different scenarios, maybe create a simple AI that would just prepare this large test set for that. But that would be it. If I wanted something more sophisticated, I'd start creating a couple of behavior trees, each one going about a different, let's say, strategy. Tactics is what you have in combat. And train my AI using that. In that way, the state vector would be, of course, much larger, but it could generalize about a greater extent of situations in the game. So yeah, it falls into the competency of the featured scientists. So basically the data scientists. They tell you how much data you need, what kind of data to go about this particular behavior that you're after.
Last question.
In case of neural networks, the larger the input you put to the system, you called it the word state,
Yes.
the more time you need to train it. And I was thinking about, during your research about the topic, did you step on some kind of a hybrid implementation? For example, we have a finite state machine, and one of the states is the decision from the state is put the neural network inside. Did you step on it, or what's your opinion about it?
To me, you asked two different questions, so let me address both of them. Okay? So yes, as the models as the data sets and feature sets specifically get larger, the training takes longer. But training is done offline. It's never done online, unless, of course, you have something like let's say a Gaussian stochastic model that will, defer which data is good and which data is bad on average. So that's online learning. So, but for most of the models, you train them offline, so there's no issue there. It's just, how you come up with samples. As for the other question, so can you mix and match? Of course, once you train the model, you can export it, and it's, like I said, it's just a matrix multiplication. So what you do with it, what behavior it exhibits, you can put it in your other code. Let's imagine Unreal having a block, This block says very good, like hard mode network, and the other one is an easy mode network, and you can toggle between them by toggling the difficulty level. Is that pretty much? Okay, fair enough. If you have more specific questions, I think we still have time, right, for questions? Okay. Leszek.
So I have another question if you remember any of your bigger experiments, could you tell us what the size of a trained neural network matrix is, how much memory one actually needs to to have it I mean any sort of real world scenario, just to have an idea of the magnitude.
Oh, okay. So first of all, I've never actually implemented anything specific for a game. So talking about how much data I would defer from a game state, I don't have an experience with that. But I worked with, for instance, text generation, natural language processing. And data sets are not that huge. It's usually a vocabulary. So imagine when you're working, for instance, with a vocabulary, with how you prepare a network for generating human understandable text. The way you go about preparing this world state is you create the vocabulary of all the words that you have, you put them in an array, and then the vector looks like there's it's called one hot vector. It's got a component for every word that you have. So for instance, let's say that your vocabulary, I don't know how much words are there in the Polish vocabulary, let's assume 10,000. So it would have 10,000 components. It would be a vector of 10,000 components that has zeros where the word is present and 1 if the word is not present. That's it. And then multiple test samples for that. Now, this state vector, let's put it, would look differently if this was a classifier. So if, for instance, I was trying to classify an email, if it's spam, if it contains spam or not, this would be then a vector. It would look a little bit different if it was a recurrent neural network, which is something that has temporal features that can pretty much remember what it said first. It's very good at modeling probabilistic models, such as language model. But general rule applies to that. So data-wise, I don't know, can't remember, 5 megabytes or something is like gets you. It's you can download the, for instance, a good data set is the database of Twitter comments, and you can, create there's even a sample online that can help you build a bot that speaks to you as if you were talking to somebody on Twitter.
Okay, still have 3 minutes, so if you have more questions, you can use it.
Don't you think that deep learning and machine learning is a bit of an overkill if you're making a commercial game with fairly simple rules for a player? And also, I want to mention that adaptive AI is present in game industry for a while now. I think that even Counter-Strike 1.6 had learning bots. So I just don't think that your remark that machine learning is something brand new in games is correct. So what do you think about that?
It's a fair point, but machine learning is not only deep neural networks. It's a lot more. For instance, PCA, which is commonly used to decide which part of the state vector matters. It's a machine learning algorithm. Machine learning refers to a group of algorithms that pretty much adapt. That's what I'm arguing. And of course, there are. And there are bots being developed for Quake, for Doom. Those are really good testing environments for that. Absolutely. And they're still doing right now. The difference between what has been added, because I'm not sure what bots are you referring to at this point, but what I can say, for instance, from what I've seen, there was a bot released for Doom last year. There's a ongoing competition running in Poznan it's called Open Doom or something like that, Web Doom or something like that, and it was based on reinforcement learning and won the competition, showed outstanding results. The bot looked like a real human being, indistinguishable. So a lot of people rule that this is like the best one there is. So of course, adaptation has been with us, but there are some limits regarding the amount of data that we can throw at it and the limits of us, basically. We stand in the way of truly adaptive thing. So if you're going about creating AI using the most mainstream approaches, at the end of the day, you're still up in the driver's seat, making decisions how to mend the data. This is the problem that machine learning goes around, especially deep neural networks. They can figure dependencies in data in themselves, for themselves, sorry.
Okay, if you have more questions, probably you'll find Piotr during after party.
Yep.
After party is here, if you are not sure, in this building. Okay, so thank you very much.
Thank you very
Huge
much.
applause.